Hello. Good morning, everyone. Welcome back. Today we have the second lecture on stochastic calculus by Professor Paulo Rufino.
Right. Thank you very much, Otávio. Good morning, everybody. Welcome back. So let's carry on with our mini course on stochastic calculus. The last lecture yesterday, we finished defining p variation. So for p greater than equals 1 and f from 0 to t going to r, the p variation of f equals limit when the mesh goes to 0 of the sum f ti plus 1 minus f ti to the power p. And I have mentioned that if it exists, if p variation of f belongs to 0 plus infinity open, it implies that p is unique. So f not necessarily continuous, not necessarily continuous, it implies also that f is bounded. Well, I leave it. I'm not going to prove. Can do it as an exercise. And we have talked about, we have defined martingales, and I have two quite simple exercise regarding that. Which says that bt square minus t in next lecture, I mean tomorrow, via Ito formula or via Ito integral, we are having a machine to construct lots of martingales. But this is still quite simple to make it to make, I mean, it handmade proof that this is a martingale. Exponential of alpha bt minus alpha t square over 2. They are martingales. And another property which I'm going to use today, and I leave as exercise, is that conditional expectation of mt square minus ms square conditioned to fu for u less than or equal s less than or equal t, that this equals conditional expectation of mt minus ms to the power 2 conditioned to sigma algebra fu. I mean, in all this case, the filtration is intrinsic. So I mean, a martingale with respect to a certain filtration f of u. This is a martingale with respect to the proper filtration generated by the Brownian motion. It's I mean, it's all intrinsic here. What is the filtration which we are considering? Okay. To prove this as a hint, use that conditional expectation of x given of conditional expectation f s given f u equals x of f u almost surely. This is a simple property for filtration for the projection which we have defined yesterday. Okay, and we carry on with a nice property, with an interesting proof of Dube decomposition, which is an extraordinary idea, extraordinary proof, or idea is almost philosophical, which says that for martingales which are continuous and non-trivial, non-constant, they have p exactly equals to 2. It could be anything, could be fractional, but it's not. It's precisely 2. And that's the reason that Ito formula has order 2 and now this theory has order 2. And again, philosophically, this is the motivation to go ahead. So why to stick in a theory of order 2 and not going beyond in a theory for p greater than 2, which is the theory we are attending the course on Routh path, right? So here we go. But before that, I'm going to give you some references on books which I'm more or less following or have some ideas. There are tens of good books on stochastic calculus, but some of them it's worth mentioning, or at least as somehow more popular. So one of them is a book by Protter, which is Stochastic Integration, and Differential Equation. Another one, which is a comprehensive book, almost encyclopedic, is Review in your continuous martingales and Brownian motion. This book has been mentioned by Sebastian Riedel yesterday in his course. It's pretty much I would say, yeah, encyclopedic and comprehensive, and lots of good exercise, and not all of them very easy. There are some, well, there are, as I said, tens of good books. And somehow choose your favorite in all the ideas, or at least the ideas in this mini course will be in all of them, and presented in one way or the other. Well, we have Karatza, Shrev, or Fabrice Baudouin. I have here a copy of Fabrice Baudouin book on the diffusion process and stochastic calculus, and well, so many others. Which is and I by myself, I have a booklet, but published still yet in Portuguese, which is a condensation of the main ideas, which is as I said in Portuguese, it is a condensation of all the main ideas of all these books with my own point of view of the theory. So it has been published in IMPA. This well, in any case, in my homepage, in IMPA Publicações Matemáticas. In any case, there is a PDF copy available in my homepage of the second or the third edition. I'm not sure. Right. So let's prove the Dube decomposition theorem, which is this fantastic result. Not yet. Sorry, not yet. Let's first prove another a preliminary proposition. Still going on this direction, which says that martingale doesn't have one variation. I mean bounded variation, right? It says if MT is a continuous martingale, in the sense of continuous trajectories, if Vt, which is the one variation of MT, mind that this is a random variable, so it depends on each trajectory. That small t here corresponds to a capital T here. So we are moving t forward and backward. Okay, so it's a function on t. So if it is finite, which we are going to call it bounded variation, classically, then MT is constant. It means we are not interested on those martingales with bounded variation. So it pushes us to look for p greater than 1. Okay, so in the proof, or all the proofs which I'm going to make today, is an idea of the proof, is 3 or 4 lines on the main idea, the main philosophical idea which is behind, without doing all the details of convergence or whatever. So without loss of generality, assume that M0 equals 0. Otherwise take MT tilde equals MT minus M0. Right? Then M tilde would be 0 at 0. Okay? So we take a partition delta 0 T1 Tn equals T, and we write the expectation of mt square, we write it as a telescopic summation. Expectation of the sum mti plus 1 square minus mti. I from 1 to n. Simple like that. We use I'm going to use the exercise, which is in there with f0, with fu equals f0, with expectation. So this corresponds to expectation of the sum I equals 1 mti plus 1 minus mti to the power 2. Okay. And this is less than or equal. This is less than or equal expectation of the summation I equals 1 up to n m ti plus 1. Is it what I mean? No, it's, I go directly to what I want. Vt, which is the bounded variation, times sup on I of mti plus 1 minus mti. Is it correct? So we isolate the sup, take the sup out of the summation. What you'll get inside is the variation, which we assume is finite. And by continuity, this goes to 0. When the mesh of delta goes to 0, right? And this is equals 0. So if the square equals 0, then the martingale, the martingale is constant, equals to 0. Mt for all t. Well, so please don't hesitate. Feel free to ask questions or make comments. We are cheating a little bit. The idea is there. It does work, but I'm cheating somehow. So when we have one comment. If we take, that's right, the limit, right, thank you. Yeah, thank you. So expectation, this goes to 0 when mesh goes to 0. Better, right? This is finite. This is for a fixed partition. So this is finite, and when the mesh goes to 0, this part goes to 0, right? What you are asking is why the limit is going to 0. That's the point which I want to. It's a good opportunity to introduce stopping time, which is more or less related to your question. What's your name, sir? Andy Algrado. Right. Okay. Thank you, Andy. Is a good question. How can we put the limit inside? So we need that it is bounded, but uniformly bounded is not our hypothesis. This is a random variable. So it has to be uniformly bounded for this argument to hold. So the proof is is somehow cheating, or I would rather say that is half of the proof, right? In the sense that we have to pay attention on the unboundedness. And that's a good opportunity to, so in this sense, the idea holds, the idea works, but I'm going to introduce the tool of stopping time, which is quite useful exactly to deal with problems like that. Whenever we have to take boundedness or any other convenient condition, we localize the problem, and the idea works. So stopping time, the stopping time here we are going to define is say tau n. So let me first define abstractly. So the definition. Probably most of you already know the definition. Stopping time is a random variable with respect to a filtration, ft. If the set tau smaller than or equal t is contained in the sigma algebra ft for all t. So typically, the examples of typically if xt continuous and adapted, tau equals infimum of a set S, such that xs belongs to A, say an open set is it, or open set, or a closed set, or F one of them this belongs to A. It enters. This is the entry time, or the heating time, of. It means it measures when something which we are interested in holds. So in our example, the stopping time we have to consider is, well, one of them can be defined as infimum when Vt omega is greater than n. Then we come back to the proof. Then we introduce the notation m tau n of t, which is m t n tau t, which means the minimum between one and the other. It means now everything is bounded, is uniformly bounded. So this process, the variation is an adapted process, and we stop when we get there. So with this rig here, and there, and there, and there, and there, and everything holds. And with this stopping time, this is still a martingale. So we are going to use this trick whenever necessary. And I show you only the main idea. I show half the proof, and you complete with stopping time. Okay. Right. Now we are in a good position to prove the Dube decomposition theorem. First, we define the quadratic variation of a martingale which may not exist path by path, but it does exist in probability in the following sense. MT, a martingale. The martingale, we define the quadratic variation M equals limit in probability when the mesh goes to 0 of the sum of M Ti plus 1 minus M Ti square. And the Dube decomposition theorem is going to state that it does exist. I show it does. We are going to prove now. It does exist. This is brilliant. There are many notations for that. Use the notation you are more familiar, the notation you like it most, depends on the books. Many people write like that as an angle bracket. Many people write as M. Choose your favorite, and mind that it depends on T. So it's a process. It's an increasing process with T. By polarization, we define the crossed quadratic variation. Crossed quadratic variation between one martingale and M and N martingales. This is half minus M minus N. So if it does exist, then the crossed quadratic variation also exists for martingales. Yes, please. Yes, good question. Yeah, and we are going to use it on when we are going to prove the Ito formula. We will need it. Thank you. So this is precisely the limit in probability delta going to 0. The sum along the partition MTI plus 1 minus MTI times NTI plus 1 minus NTI. Right. And please interpret this limit in probability in the sense that not all trajectories or not all path by path is conducted, but those which are well behaved in the sense of this Riemann summation, if we call it as Riemann summation, if not all, the set where it doesn't follow is as small as you wish. In this limiting probability. So finally, the Dube decomposition. This theorem Dube decomposition. It holds in a more general context that I'm going to present. It holds for sub-martingale, but I'm not going to mention this. I'm just going to prove not the simplest, but well, the common known version of the Dube decomposition. So in some sense, one way to state is the following. So if MT a martingale non-constant, otherwise it's trivial. One way to state is that P equals 2. So it's already a fantastic result, since given a certain function, is not always easy to say what is the P, the correct P to calculate the P variation. This is one interpretation. This is all going to be in just one simple proof. Simple, yeah. Well, few lines. You are going to see that in few lines we get all this at the same time. So P equals 2. It is going to be proved that the quadratic variation has one variation, which we call bounded. Once, as I said before, bounded variation. So whenever we take the bracket, the bracket or the quadratic variation, it is going to be a process with bounded variation, including the crossed one, since it is by polarization. It is a summation of quadratic variation of martingale with themselves. Okay, and thirdly, this starts at 0. So obvious. So when t equals 0, it vanishes. It is increasing. Also obvious. And the most important, the technical one, which is in stochastic analysis more important property, is that this is the unique process such that the square of the martingale minus its quadratic variation is a martingale. Right? Most of books, and this is unique. Unique with properties above. I mean, unique as bounded variation, increasing process starting at 0. Right? So normally, so to prove this, all the rest comes for free, as I said before. So let's prove this decomposition. As I said before, if M is a sub-martingale, which means that the conditional expectation is smaller than or equal the process itself, it also works instead of M to the power 2. Yes? Sorry? Not yet. I'm not sure. So the version I have prepared thinking on continuity, but I think that it's not really necessary. We can check it by the end of the proof if this holds. It's a good question. That's it. Right. Yeah. Yeah. That's what I mean. That all martingales have a 2 variation. All non-trivial martingales. Right. So continuity is say I prove the continuous part, which is easy, and then we, as an exercise, we think about discontinuous process martingales, like Levy process and so on. But so I'm just going to be safe here. Right. Again, proof or idea. For uniqueness, start with the easiest part. So if m squared minus a, this is a martingale. This is a martingale with A and B increasing adapted processes. And if they are increasing, they have bounded variation, right? Martingale minus martingale is a martingale. Is a martingale with bounded variation. And we have just proved in the previous proposition that martingales with finite variation or bounded variation, they equals to 0. Then they are constant. If they start at 0, they are going to be constant, equals to 0. The martingale part. I mean, to prove that this is a martingale. So we are going to take a partition . Zero. S T. We have here T J Tj plus 1 becomes up to tk plus 1. These are the elements which are relevant for us. So without loss of generality, for S greater than 0, smaller than t in this configuration, and we define a proxy of the finite variation, which is t delta t. This is the notation, which we are going to call. We are going to define as from 1 to k. K is one immediately before small t, which is mti minus mti minus 1. So we are adding over all the elements in the partition plus this small bit. This is the summation plus the small bit, which is mt. This is all to the power 2. Plus mt minus mtk to the power 2. So of course, when the mesh of the partition goes to 0, this tends to the quadratic variation if it exists, right? But I am considering a fixed partition delta. The point is the following. We are going to prove that mt square minus t delta t is a martingale. Is it believable? Does it contradict the uniqueness? No. T of delta is not necessarily increasing. There is this small bit at the end, which is not guaranteed to be increasing, right? So it's almost, as I said, is a proxy of the quadratic variation. But this is good enough to prove that this is a martingale. And then when we take the limit of the mesh, the limit of the mesh is going to be the process, which is the quadratic variation, and then p equals 2. So the convergence exists, p equals 2, and this process has one variation. That's the idea. So in a single calculation, we conclude all these three conclusions. I find it really very clever. This is foundational results on the theory of martingales, which Dube is one of the beginners of. He introduced it. To one of the mathematicians who introduced martingale theory. So let's prove what I claim. We are going to calculate the conditional expectation of t delta t minus t delta S conditioned to f of S. Of course, TS is FT adapted. Is constructed up to time TS, and all the ingredients are FS adapted. And well, if we take the definition, itself, I'm going to start with write the small bits on the left hand side and on the right hand side. Firstly, so this is ms minus mtj minus 1 square plus the right hand side very last bit mt minus mtk to the power 2 plus summation I equals j up to k mtj plus 1 minus mtj square conditioned to sigma algebra fs. Are they all there? Probably. This left hand beat, this beat, and the summation between tj plus 1 minus mtj I here. Sorry. Is it okay? And now comes the clever idea of Dube, which starts with the exercise I put at the beginning of the talk, of the lecture, that for martingales, the square of differences are the difference of the squares. And then we can make a fantastic telescopic cancellation. And what we get here is expectation of there is something. The sign has some problem. Could you help me to fix this? Minus ms square given fs. Right, thank you. T j plus 1. Does it solve? Is that? Say again. In front of the brackets. Yeah, it comes here, it comes there. And changing the order. Right, okay. And thank you for helping with this. And then after this telescopic cancellation, we have that. Is it okay? Outside the expectation. Which bracket? Well, can I just leave us an exercise? But it's consistent. The argument is consistent, and I'm sorry. You all can fix. After it's here. Minus S T J. Right? Are you happier? Well, thank you very much. I'm sorry for that. In fact, I should follow strictly what I have. Yeah, if I had followed strictly, would be okay. Right. This is a fantastic idea of this telescopic calculation, which comes out of the exercise. Well, this proves that if we by linearity, it proves that exactly what we want. That mt square minus mt is a martingale. So it implies that conditional expectation of mt square minus t delta t conditioned to fs equals ms square minus t delta s. Fantastic, almost surely. Right. So and the last observation is that T delta is not increasing, as I mentioned before, but is going to be when mesh goes to 0. So, and T delta T converges to when mesh goes to 0, converges to the quadratic variation at T, which is increasing. Okay. Right. Corollary. M times M minus Mn. So Mn is a pair of martingales. This is a martingale. One easily proves by polarization. Example. It's not quite long, but interesting calculation, which I'm going to leave as an exercise, that the quadratic variation of Brownian motion, B equals T, almost surely, as usual. The hint just prove that the norm for a summation given a partition B Ti minus 1 minus B Ti square minus t converges in L2 of omega converges to 0 when mesh of the partition goes to 0. And if we have convergence on L2, we have convergence P almost converge the convergence in probability as well. Okay. It's a nice calculation which includes all the properties of martingales, of Brownian motion, which you have mentioned yesterday and today. Okay. I'd rather skip this proof. It's good to. So before I finish, before we change to stochastic integration, I just want to mention, without proofs, a couple of results on martingales, on convergence of martingales, which is quite not only interesting but important, if not proved, at least to be mentioned. I'm not going to use it directly in this mini course, but it's worth mentioning. Classical results. Just a couple of them, photo properties. Properties of martingales. Drawing theorem. Again, Dube inequality. Xt continuous. Regarding the question on if it has to be continuous or not, we clean without re-examine the proof. If it's, well, check if it's really necessary continuity. So Dube inequality, Xt continuous for P greater than 1, then lambda P is a version somehow a version of Chebyshev inequality, smaller than supremum on T of X T to the power P, and for P strictly greater than 1, we have that supremum on X and T. Norm in LP is smaller than P minus 1 sup on T norm of Xt. So this is extremely useful and in stochastic analysis. Secondly, Xt bounded in LP. This is a convergence. P greater than 1 is a fantastic result on convergence. Then Xt converges almost surely to a random variable x infinity. Almost surely. This random variable belongs to LP. And look, this is the generator of the whole martingale. It's conditional expectation of x infinite filtrated at ft almost truly. This is really fantastic. Yes, question. In the Dube inequality, which line? The first inequality. Here. Yeah. You're right. Here. Expectation is like that. Inside the supremum. This. Right. But I'm not sure. I will check. I'll check later. All right. Thank you. So this is and for p equals 1. For p equals 1, we have the same sort of result, but we need uniformly integrability. So if we have limit on k going to infinity of sup on t xt p for x t greater than k. This is the definition of uniformly integrable. Uniformly integrable. It means the integral does not spread somehow. When we increase k, we are killing the mass is somehow concentrated. Yes. In the first line. So you mean supremum of so, or this to power p. Right. Okay. Thank you. Yeah. Yeah. You're right. Thank you. I am somehow making a comparison of. So this is. The results I want to mention without proof is Dube inequality and convergence of martingales. In this sense, for p strictly greater than 1, and for p equals 1, uniformly integrability is equivalent to what is written up there. Is it understandable? Is it okay? What I mean everything here is repeated down there. So either bounded in LP for p greater than 1 or uniformly integrable is equivalent to convergence almost surely in LP and random variable which generates the martingale. Okay. Right. Well, it's a side result. I'm going to introduce the stochastic integration now. Yeah, I got it. Yeah, thank you. So this stochastic, or rather the classical Ito integration. So I'm taking MT, a martingale, which is going to be the integrand of our process, and we call XT a simple process. Or elementary processes. Elementary process. There's a filtration FT. Process XT equals 1, 0, T1, X0 plus I equals 1 up to N 1 open T1 TI TI plus 1 open here applied on T X I such that Xi are FTI measurable. It's a process which is constant, and it jumps at a certain partition. It jumps to random variables at a certain partition of the interval 0, 0 t. And then the integration for this process so the first definition is that the integration of this process with respect to MT S is a new process. It's a new process given by from I equals to 1 up to K X Ti M Ti plus 1 minus M Ti plus xtk mt minus mtk. Tk if tk minus 1 less than or equal tk. So when t is in the interval tk minus 1, tk is so this is the Riemann sum, and it's easy to prove that it's a martingale. A proposition is that xt x gm is a martingale. So this is the key point of the Ito integration with respect to martingale, is that it is again a martingale. So it's not difficult to check. It's conditional expectation applies to this. What is a key point here is that we are integrating with respect to the left-hand side of the interval of the partition. This is a question. Can you louder, please? So sorry, I can't. It depends on xt. I'm sorry, I can. Ah, right. Okay. So, I'm sorry. That's it's a bad notation. That's good point. Bad notation. Maybe I should write x with a super index instead of subindex, and then xi are fti measurable. So they are random variables. Okay, it's clear now. That's the question. Okay, thank you. And dependence on t is here. So you sum or you don't sum if it is depending on the depending. In fact, is the sum is here is not necessary. It's either in the interval or it's not. Doesn't play a function here. And the sum is here. So we are integrating step by step this elementary process. Right. I is an index. No, we don't. No, I'm not integrating. I am just defining that in this interval, it is a random variable which is measurable at 0. At time t1 is this is x0, this is x1, here is x2, and so on. And this is selecting which interval each interval t belongs. Okay? We just have one jump, right? Say again for. Ah, I got it. Right. So, right. Thank you. Thank you. It's for a fixed I. So thank you. Sorry. You were not confused. I am confused. Thank you. Right. From 1 to, well, whatever, to infinity or whatever, or to k, right? Thank you. Yeah. I have to change the notation there. I'm putting super index there. Thank you. Right? I'm still looking for the future. Well, first of all, let me just write like this. I. X I XK XK. Thank you. Great. And the rest is okay. Right. Thank you. This is a key point. Yes, is a key point that we are integrating, taking the element of the integrand on the left hand side of the interval always. Otherwise, it's not going to be a martingale. And the Stratonovich, or Stratonovich, as Russians used to say, Stratonovich equation, we don't take the left-hand side, we take the average of the right and left-hand side, and it's not going to be a martingale. So this is a key point, and I am not going to prove. The point is to see the last bit. So this is constant, measurable, and when we take expectation, it holds. We cancel out what is not measurable, and it does work. Yes, Beatrice, please. I'm sorry. Partly is the acoustic, partly is the masks, and partly is my hearing, which is not very good. Yes, after we revise, should be up to k minus 1. Is it? Is it k minus 1? Then it goes up to tk minus 1. That's right. Thank you. Yeah. Now it's... I equals to 0 to start with ti plus 1. Right. Thank you. Right. And the full definition is the limit in probability of this sum. So for adapted process xt, adapted integrability conditions So I'm anticipating. So I introduce this integrability in 2 minutes. then the integral from 0 to t of xs gms is precisely what the Riemann sum, the limit in probability of the Riemann sum. X, taking the care that is on the left-hand side of the interval, mti plus 1 minus mti. Well, whatever. I leave it open, not to write wrongly. I leave it open, and you adapt it if you start with 0 or not. If you allow. Thank you. Right. When it exists, right? And let me talk about this integrability conditions, which is interesting and leads to the Ito isometry. So essentially, what I am the proofs which I'm going to do both for Ito isometry and for quadratic variation of stochastic integral. I'm going to do for elementary processes, and then just take the limit in probability, right? So this integrability conditions. Is that x belongs to, for all omega, belongs to L2 with the measure given by the quadratic variation of m, which induces a measure. It is an increasing function. It induces a measure on R, and moreover, and expectation of the integral from 0 to t x, say explicitly omega here, integrated with respect to the quadratic variation. So this is a short way to write the quadratic variation. I think everybody is. I hope everybody's following me, right? There's a shorthand. And quadratic variation, which is this bilinear operator. When there was a question about crossed variation, this is a bilinear in some sense positive definite in some sense. And we assume that this is finite. So it belongs in that's to say that x belongs to L2 of P times GM. And here comes the Ito isometry, that stochastic integral, Ito stochastic integral, is an isometry between this space and L2 of omega, or L2 of P. This is the theorem. Ito isometry. From L2 right. So what we do is in 2 or 3 lines we prove we prove for, or we are going to prove just for elementary processes, which is, and then take the limit. Proof. Well, it's not the proof. It's the idea. So we want to prove that expectation of this random variable XS DMS equals that one, 0t x square dm. On the left-hand side, is expectation of the sum ij x. So from here to there, I changed it. Well, you notice I changed completely the way to write. Since here this xt can be any process, no elementary anymore. So this is xti, xtj for a certain partition, mti plus 1 minus mti, mtj plus 1 minus mtj. Is it? Yep. I'm taking this summation, taking the square. And note that it vanishes if I is different from j. The term vanishes. Why? Take conditional expectation, and then this one term vanishes if we take the appropriate conditional expectation. So they equalize. So what is remaining is expectation of the sum of xi square, xty. Xti square mti plus 1 minus mti square. Which converges well with some extra. It does converge to the right-hand side, to this. And as a remark, some books take many among those tens of good books on stochastic analysis. Some of them prefer to prove this Ito isometry to prove that instead of this definition of Ito integral, to prove Ito isometry, to prove that elementary processes are dense in this space, and then the stochastic integral is given by the limit of this process. So it's another way to introduce what I was planning to do today was a little bit more than that. I'm just give a hint. So tomorrow I restart proving the following: that the quadratic variation of a stochastic integral of x dm and y dn for two different martingales and two different integrands, the quadratic variation is given by the following bounded variation process: is x times y integrated with respect to the crossed variation. This is, again, a fantastic and quite useful result, part of a stochastic calculus. I intended to do it today, but the time is over, so we restart tomorrow with this formula. And this formula and Ito formula, and Stratonovich, as the Russians prefer, integration and Ito formula for Stratonovich. Okay, and okay, thank you very much. Any other question or comments, remarks? Okay, so thank you. See you tomorrow.
So, how did you go from this line to this line?
Let's start the exercise class of stochastic calculus. Our teaching assistant is Lorival Lima. Please.
Hello, everyone. Okay, my name is Lorival Lima. It's pretty nice to be here and have the opportunity to talk a little bit about stochastic calculus with you guys. And I have been speaking with some of you, and I think you guys have a really nice background in stochastic calculus, and some of you really interested in research on it. And that's really nice. And I brought some questions, some basic but interesting questions, so we can discuss together. So if any of you have some questions or contributions, or I don't know, just stop me anytime, okay? All right. The first question, I don't know how to hold the microphone and my notes at the same time, but all right, let's try this way. Okay, the first question is prove that the quadratic variation of Brownian motion, B, it's a Brownian motion, okay? This is actually equals T, okay? So any of you have some idea how to solve it? Okay. I think we are going to start by definition. First of all, we have to define a partition. Okay. So solution. That pi n. Okay. Pi n be a partition and let's define kind of a process un as the summation of b t plus ti plus 1 minus b t y, okay, square. Then I want to study actually the convergence of un minus t, okay? So un minus t is actually equal the summation of b t y plus 1 minus b t y square minus ti minus 1 minus ti. Okay. All right. So this term here is my time with respect to the partition Pn, pi n, okay? All right. So there is something really interesting that we have to notice is that note that this expression right here would be b t I plus 1 minus b t y square over t I plus 1 minus 2y. Okay. Can you guys see something special about it, about this expression? I'm sorry? Yes, yes. It's nice. This actually has the same distribution of a random variable z square, okay? Where z is a normal with mean 0 and variance equals 1, okay? What else? Okay, then we just do some calculations, okay? Then we have that the expectation of un minus t, okay, square is equal the expectation of b t plus t I plus 1 minus b t I square minus t I minus 1 plus 1 minus t I. Okay, all this expression squared. Okay. Okay, but I can rewrite this expression as this. Okay, so this will be z square. Where is z? Z. What is a z? It's a n 0, 1 random variable. Okay, so there will be z squared minus 1 squared times this summation. Okay, of t y plus 1 minus t y squared. Okay, now what's going to happen if we narrow this partition, the partition pi n? What's going to happen with this expression? You guys don't speak too much, right? Okay, if I narrow the partition, if mesh is going to 0, the partition, this term actually is going to 0, okay? All right, so this is integrable variable, okay? So all these expressions have to go to 0 when n is going to infinity, okay? So when n goes to infinity, it follows that the quadratic variation of the Brownian motion, which is defined as this limit when n goes to infinity, the limit of un, the process I defined, this has to be equal t, okay? All right? Okay. Does anyone have any questions? Okay. All right, next question. So let's y, x and y be independent. Dependent random variable. Okay. Prove that the induced probability of x plus y is equal the probability induced by x times or convoluted by the probability induced by y. Okay? This asterisk here represents the convolution defined by, if you have two measures mu convoluted by eta, that will be over a set A that is actually is going to be the integral of a probability space of eta of A minus a point x d mu of x. Okay? Okay, the idea here is to define a new variable, okay? So let z is a new variable which is defined by this sum, x plus y. Okay. Then for all a set in Borel of an Euclidean, one-dimensional Euclidean space. This is the space we are working. We have that the probability induced by z in A, this is equal the expectation of one function of the set z in A. Okay? So everybody is familiar with this notation, right? Yeah. Okay. Okay, but this is equal the integral of the probability space of 1 of x plus y in A, okay, times the probability induced by x plus y, okay, dx dy, okay? But remember that those random variable, they are actually independent, okay? So by independence, we have that we can rewrite this integral by this double integral right here of 1 over the set x plus y in A with respect to the probability induced by y dy and the probability induced by x dx. All right? So far, so good, right? Okay. Okay. Yeah, I can rewrite that as the double integral of omega of 1 over y, which is in A minus a point x is the random variable in the point, okay? Of p y dy px dx. This is okay. We have to notice something. This integral right here. Okay, this integral right here. This is actually the probability induced by the variable y. Okay, on a minus x. So we can rewrite this expression as the integral of omega of py over the set a minus x with respect to the probability induced by x dx. Okay. What is it, guys? What is it? What? Deconvolution. Nice one. Yeah. This is actually the convolution of px convoluted by py over the set A. Okay? Yeah. If you work with probabilities and conservation of laws, I think you might apply this once. I don't know. So, okay, next question. Is immediate, yeah. But I just want to, I don't know. It's more fancy, you know. But, I mean, Paulo Rufino told you guys about if you have two random variables which are independent, so the characteristic function can be written by the multiplication. Really? Okay. He didn't. Yeah. Okay. All right. So here we consider x1, x2 up to xn be random variables. Such that the mean of xn is a constant m, okay, and the variance. I'm gonna use this notation for variance, okay? And the variance of xn will be less or equal sigma square. So the question is, prove that for all epsilon greater than 0, we have that epsilon square times the probability of this expression here, it's a big one. He's saying. Okay, the probability of this expression is less or equal the expectation of the same expression, almost the same. Which is less or equal sigma square over n. Okay, so the challenge is to prove this expression here. Okay. Okay. Do you guys have any clue of how to do it? Yes. No clue at all. Sorry? Yeah, it can be. Yes. Yeah, it's the same of Chebyshev inequality as well. You can use it, right? Yeah, okay. All right, so let epsilon be greater than 0. So you apply actually the Markov, or you can apply Chebyshev inequality. Okay, for P equal 2. No, it's sigma. It's, yeah, sorry. Suppose it's a sigma, okay? Yeah. Okay, okay. my 6 and my sigma is the same thing, okay? So sigma, okay? All right. Okay, let's see. Okay, okay. I think it's directly. If I apply this inequality, actually you have epsilon square. This is not a this is not a e. It's a epsilon. Epsilon square times the probability of 1 of n times the sum j going to n of xj minus m. Okay, greater or equal epsilon. Okay, this has to be less or equal the expectation of 1 of n. Okay. Yeah, that's the first part of the inequality. Okay. So we have already this part here resolved. Okay. On the other hand, okay. By independence, it follows that here we have the expectation of this expression this is actually the variance, okay? I'm applying just the definition of variance, okay? With respect to the definition of the variance with respect to the expectation, okay? So that will be 1 of n, the summation of x j minus m, plus the square of the expectation okay, of this expression. Okay. Just the definition of variation, okay? Okay, guys, look to this expression right here. What can you tell me about it? What can you tell me about it? Okay, just remember that the expectation of xn is equal m is what? 0, okay? Because this is going to finish because here we have an n, okay? We have 1 over n multiplying. The expectation will go inside this expression here, the summation, because it's a finite sum, and the expectation of xj is equal m, we have to do minus m here, okay? So this is going to vanish. Okay, so we have that, we have to work just with this expression here. Okay, so this will be equal 1 over n squared, okay? Because we have n, 1 over n inside of the variation, so when you pull out, it will be squared. Okay? So 1 over n squared times the variation of the sum. Okay? So the variation will go inside. So the variation, we have the variation of xj. The variation of xj is less or equal sigma square, not 6, sigma square. So you have that this expression is less or equal n sigma square over n square. Okay, this is actually sigma square over n. Okay. That completes the second part of the exercise. Any questions? Any comments? Yeah. Yes, it's independent. I think, yeah, sorry for my, yes. Yeah, I didn't put it, sorry. Those variables, they are independent, okay? Equally distributed. Okay, sorry. Any more comments? Okay, next question. Prove that there is not translation invariant probability measured in this space here, C01 or okay. Borel of C. Okay, that's it. Okay, the next challenge is prove that is not a translation invariant probability measure in this space here. Okay, the space of continuous functions going from the intervals, closed interval 0, 1 up to our Euclidean space. Okay, and this is the Borel It's the sigma algebra, Borel sigma algebra. Okay. So do you guys have any clue? Yeah. Sorry? Markov. Markov. Okay. Sorry. Yeah. I think someone here told me. Yeah, it's Markov. Actually. Equals 2 is what? It's Markov for P equals 2, right? So, but they are, yeah, they are actually the same, but Markov is more of a generalization, right? Yeah. But okay, Markov or Chev. So, do you guys have any clue how to solve it? What time is it? Guys, I'm so excited to I'm really excited to talk about it, all those stuff that I'm lost in the time. Okay, maybe we have just 15 minutes. I'm really sorry. It has been so much fun. Yeah. Okay, let's go. Okay, the idea here is to. I actually was trying to solving this question, but I have just one way to do it. If you guys think in another way, just let me know, okay? Because I don't know. Yeah, I always think the idea is you suppose that actually exists, okay? Probability measure in this space. Suppose that the exists a translation invariant probability, okay? Invariant probability in this space. So I will call invariant probability P. Okay, pi, P, I don't know, P. Okay, then we consider this set here. We consider B, which is equal F in C, 0, 1, or such that this happen, okay? All right. This space here, B, is actually a compact subset, okay? So if this is a compact subset, then B can be covered by a countable and finite collection of disjoint sets B with center Fn and radius epsilon. Okay. So this is a collection. Okay? All right. So since P is invariant, by translations, okay? There exists beta in the interval 0, 1 such that the probability of B of those collections okay, is going to be beta. Okay, so far so good. Everyone agree? Okay. Yeah. Yeah. Actually, you just choose it exists on beta in the interval, and by translation, you can do a translation by the probability measure in such a way that this is going to happen. Okay. Because the probability is invariant by translations. So you can do that. Okay. So this is true actually for all natural n. Okay? Then we have that the probability of B is greater than or equal the probability of the union, the infinite union of n, the infinite union of B Fn epsilon. Okay, so by probability property, this is actually a summation of n, which goes to infinity of the probability of B Fn epsilon. Okay, but this is beta. What's going to happen to this expression? This is infinity, right? So this is actually infinity, but it cannot be infinite because it's a, sorry, yeah. Yeah. It's because this is a compact subset. It's at least finite, right? Yeah, but it's at least finite, right? I mean, I can cover it. Yes. Yes. Yeah. Okay. Okay, I will fix it maybe. Okay, but the idea is actually that this is going to infinity, so it cannot be a probability measure. So this is an absurd, right? So it's solved. Because it's invariant by translation. Yes, yes, yes. So the idea is that this is going to infinity and that it's an absurd, okay? All right, so I will fix it. Thank you very much. This is really nice. Okay, so do you have a time for one more? No. Okay. Thank you very much, guys. It's nice. Just a thing. My friend here, Jesus Correa, he's going to take you guys to the restaurant today. Okay. Just follow his lead. Thank you. Thank you very much.
Hola. Hello. Hello. Okay, 2 minutes.
¿Qué tengo que decir? ¿Presentar esto?
No, presentalo a él.
Ah,
Sí, que se la. You are the chat.
ok.
Cuando él termina, pregunta.
Ok. ¿Y me puedo sentar ahí? Let me know when.
Yeah, so I think we have 2 minutes.
Martin. And when you finish the presentation, I come back and I take questions, right? It's 2 o'clock, so. Okay, thank you very much all for coming. So Sebastian Riedel from Bern University is going to continue talking about rough paths today following yesterday's lecture. Thank you very much.
Okay, thank you, Martin. Yeah, so yesterday we talked about Young's approach to solve stochastic differential equations. And one of the main theorem was that one here. We discussed that in the last part of the lecture. And in the proof, I was at some point I was a bit quick, so I was a bit sloppy, and Martin talked to me then, and I had a question, and indeed, so I should have been a bit more precise. So I wrote a new version, and you will also, maybe you already got it by WhatsApp, so you will get a new version of this course here. And so since this theorem is quite important, we will see it also in the last lecture when we solve rough differential equations. I thought it's maybe useful to come back to this theorem for the moment, and let me explain you what are the differences to last time and where you have to be a bit careful. And okay, first of all, the statement is still correct, of course, but the proof one has to be a bit careful. Yeah, so we want to use a fixed point argument, so as before. And so we restrict ourselves to a possibly smaller time horizon. So this is the T0 here, and so we define this map. This map is in the alpha Hölder space, and we already saw last time that yeah, so when you apply a function which is sufficiently smooth, here this sigma, to a alpha Hölder path, then the resulting path is still alpha Hölder, so you can make sense. No, we did not prove it, but this follows from the Lipschitzness of the sigma. And anyway, you can make sense of this integral since both of these functions are then alpha Hölder, and the alpha is assumed to be greater than 1/2, and so the Young integral makes sense here. And yeah, so you can define this map also from the space of alpha Hölder functions starting in a particular value. Y was the initial condition of the equation. And we want to show that this is a contraction. So this was actually exactly the same as last time, but now we have to be, it's a bit different. So we will not consider the whole space, but we will restrict ourselves to a smaller closed set, the unit ball around Y. So it's all path here in this space where the alpha Hölder semi-norm is less or equal to 1. Okay, so this is a closed space, so we can also define, so we want to perform a fixed point argument on this space now. But of course, what we have to check now is that the M, so our fixed point map leaves this small ball invariant. Yeah? So we want to prove that it does not only map to the whole space, but also to the ball again. Okay. So, and to do that, well, we have to estimate the norm, of course. So, okay, you quickly realize, okay, they have both the same initial values, so this is not a problem, but what we have to show is that the alpha Hölder semi-norm is also less or equal to 1. Yeah? And this is done here. So we use just the definition, the first line of this map. So we look at the Hölder norm, and then we use the Theorem 15. This was the theorem which provided you a bound for the integral, yeah, for the Young integral. So we use that in the second line. So you have the alpha Hölder norm, and then the supremum norm of the integrand. We talked about that also last time, why the supremum norm pops up. Yeah, and then you just use some elementary properties here in the third line. So you can estimate the Hölder norm by the C1 norm of the sigma times the Hölder norm of y. So and now you assumed that the y itself has a Hölder norm less or equal to 1. So in the next, so this bound actually does not depend on y anymore. In the next line, so I'm always with this constant, I'm a bit lazy, so I always write c, but c's here differ. Yeah, they can differ, but they are not. They depend on some of not on the relevant, so on the unrelevant things in this estimate. So, for example, here in the last line, the c will depend on the norm of the sigma here also. Okay, and yeah, so x is the alpha Hölder norm. So, and now we have to make sure that this alpha Hölder norm is small. Namely, we have to make sure that this is less or equal to 1. And so we do the same trick as last time. So we are not considering the alpha Hölder topology, but we look at the alpha prime Hölder topology. So alpha prime is a bit smaller than the alpha. Repeat the calculation, and then we can indeed show that this here goes to 0 when I make the time small. Yeah. Okay. So that we do here, and then finally we can conclude that this map really maps from the unit ball to the unit ball for small t0. Okay, and now we show that this is a contraction like last time. So we take the difference, which is just the difference of these integrals here, then we bound these integrals with the bound for the Young integral as before. Now see, I changed the alpha to alpha prime here everywhere because we do everything now for the alpha prime topology. And so, yeah, so then we have two terms here we would like to bound. First of all, this one here and then this one. So for the supremum norm, it's a bit easier. For the supremum norm here, we can bound by just taking the initial condition plus, so you have better do the calculations on your own. Then I think this is really, it's not hard to see that this is true here. So what remains, and then, okay, remember that both here have the same initial condition, is the y0 and the y prime 0 have the same initial condition, so this vanishes. So what you're left with is the alpha prime Hölder norm of these sigma y, of the difference of these two. Okay, and then, so what remains now, here also you have this, the difference of these two functions here in the alpha prime norm. This we have to estimate here as well. So let's do that. And this turns out to be a bit, so I told you last time that this is a bit, well, delicate, or there's at least some calculations you will have to do. But fortunately, we can rely on this lemma here, which tells you that yes, indeed, you can define, you can bound this difference here, but not only by the difference in the Hölder norm, and this is what you said last time, this is not correct, but what you have to add here, then it's correct, is the initial condition here also. So this is the general the general result, and you can find the proof here. And there's also a constant, and this is the constant here depends on a k, and the k is a bound on the Hölder norm of these y and y prime here. Yeah, and this k. So last time I didn't write down that, and this is the reason why we now introduce this unit ball. Because when we introduce this unit ball here, we know that this k is actually okay. This is terrible. Oh my god. So no. Okay, thank you. So yes. Okay, so we were here. So yeah, but since y and y prime are both in this unit ball, this k here can be chosen equal to 1, capital K. So actually this constant here will not depend then on the y or the y prime, which of course would not be good. And that's why we introduced this unit ball again. Okay, but the rest then is the same. So we choose, now we already work with a alpha prime topology, so we can choose the T0 smaller again if necessary. So this is a contraction. So we get and the rest is the same. Yeah, so we get a solution on 0 T0, and then you proceed, glue together solutions, and then at the very end, you realize that your solution lives actually in the alpha Hölder space, not only in the alpha prime Hölder space. Okay, so this is what I wanted to show to you now, and we will now continue with course number 2. Can you maybe do that from there, or can I do it from here? No? No. Maybe here. Okay. How's the big screen? How can? Okay, thank you. Okay, so and let's continue with course number 2 today. So we have the title is rough path. So we will actually really look at rough path today. Then a theorem, an important one, it's the extension theorem, and then we will be able even at the first step we will be able to solve at least on informal level, say linear rough differential equations. Okay. So, but first, so this is the content of the lecture. First, we will look at there are a few quite, I would say, remarkable counter examples or impossibility results, which are very general. They're proven by Terry Lyons, the one who invented the rough path theory, and that show you that there's really a problem and somehow justifies all this theory, all this work, all these complicated things you have to do later on, because they somehow show you that there's not an easy solution. You can, like, for example, the Young approach. So I would like to start with these impossibility results, and then linear equations, rough path. There's also the extension theorem, and then at the end I will discuss Brownian motion as a rough path. Yeah. Okay. So last time, or a few minutes ago, we saw that you can make sense of a stochastic differential equation of this form here, provided that you know that your stochastic process, that the x has sufficiently smooth path. And this was the sufficiently smooth, it means that you know that this process has half alpha Hölder continuous trajectories for alpha larger than 1/2. So now you can ask, okay, what about the fractional Brownian motion? So we know that it's alpha Hölder, and exactly in this regime for the h, the Hurst index larger than 1/2. Maybe can I also do it? So there may be another theorem which tells me maybe the Kolmogorov-Chenchov theorem was not sharp here. maybe can I obtain a better regularity? And in fact, this is not true. So this proposition here tells you that actually the Kolmogorov-Chentsov theorem was sharp in the case of the fractal Brownian motion. So the FBM does not have H Hölder continuous trajectories, and H is the Hurst index. So for example, the Brownian motion does not have 1/2 Hölder continuous trajectories. You might know that also. It's not easy to prove that, I have to say, but at least I don't know an easy proof, but this is how it is. So we cannot use the Young approach for the fractional Brownian motion. In particular, we cannot use it for the Brownian motion. Yeah? This is, of course, very unfortunate because the Brownian motion is the process that interests us most. Yeah? It's the most important process, and the stochastic differential equations, or most of them, are formulated with the help of the Brownian motion. And since Young's theorem, or pathwise, this pathwise theorem from Young does not work, this is another explanation why give an idea why Ito's theory is so important, is so valuable. Yeah? Because with this you can do it. Yeah? That's quite surprising that you can do that. Okay, so what you could think of now? Well, we saw the Young integral. Yeah? So maybe you could think of maybe the Young integral is not powerful enough. So maybe there's another notion of an integral which is able to deal with alpha Hölder path with a smaller Hölder index. Yeah? And okay, or I mean, you can even ask a more general question. You could say, well, maybe alpha the Hölder topology is not the right one. Maybe there's another topology I can look at. Yeah? So there's also other topologies that, there are other topologies that may describe the regularity better of stochastic processes. So for example, I mean, maybe you learned a bit about the p-variation topology. This is also a way to describe regularity of a certain path. Okay, thank you. Okay, so whatever topology you want to choose, yeah, the important thing would be that your integral, at least what you want, would be that you are able to integrate Brownian motion somehow. Yeah? So whatever topology you choose, you would like that the Brownian motion somehow can be defined on the space with this topology. Okay, so this is the minimal requirement. And there's a definition which was given by Lyons, which is quite general in this regard. So he defines, so let's take any space of path. So this is E, so real valued path here. Yeah? And let's take two series here, Cn and Sn, of independent standard Gaussian random variables. Let's take trigonometric functions here, small cn and small sn, and then we make a definition. We say that on this space here, we say that this space carries the Wiener measure if and only if, first of all, we want that at least these trigonometric functions live in E. Yeah, so trigonometric functions, well, they're quite natural, a smooth function, they should live in the space. And a second, that this series here converges in E. So E, we didn't say anything about in which topology, so this is all included in E, almost surely. Yeah. Okay, so why is this somehow a good definition, or why did Lyons choose here carries the Wiener measure? Why did you call it like that? Well, let's look at an example. So let's look at, so W will now denote a real valued Brownian motion. And then you can look at a random Fourier series like that. So this is a random a random Fourier series. It's random because you have here the Sn. This is the same Sn as before. So these are standard Gaussian random variables here. And then you have the Fourier coefficients and n. And you can prove, it's not so easy, but you can prove that this series here converges almost surely uniformly in T to a stochastic process that one calls the Brownian bridge. So this is the Brownian bridge. So what is the Brownian bridge? It's a bit like the Brownian motion, but the Brownian bridge starts in 0. Yeah, everything is in 0, I think, here. Yeah. And ends in 0. So this is the Brownian bridge. And this expansion of a Brownian bridge, you can also go the other way around and write down given a Brownian bridge, and you can use this Brownian bridge to write down a series. And this series expansion is then called the Calhoun-Löw expansion of this Brownian bridge. Okay, notice here that the Brownian bridge is the sum of a Brownian motion plus something which is smooth. Yeah? TW1 is a smooth function. Okay, so this was this we can say about the sine series here. We can also say something about the cosine in this definition of what does carrying the Wiener measure mean. So also this cosine series here converges uniformly, almost surely, to something which is called mean-centered Brownian motion. Yeah? So this is that one here. So Brownian motion minus, just a number, a constant. Okay. Also, a constant is, of course, also smooth. And in total, what we've just seen is that the space of continuous functions here carries the Wiener measure. Because putting these two things together, we've just seen is that indeed this series here converges, we saw in the beginning, converges almost surely uniformly to some process. Yeah. And you can even show more. You can prove that it converges in any Hölder space, here, provided the Hölder index is smaller than 1/2, but it does not converge here in a Hölder space in a smaller one. Yeah? Okay. So this is somehow a very general definition of what a space should satisfy, that I'm to be able to define a Brownian motion on it. Okay. But then there's this theorem, and this is this kind of meta theorem, which tells you if I have such a space that carries the Wiener measure, so it has to be large enough. It has to be large enough. But then there is no bilinear map here such that this bilinear map, first of all, coincides with the integral and is continuous. So there's no this bilinear map, of course, would be the candidate of the integral. Yeah? You integrate one path with respect to the other. Yeah? And this theorem tells you that, you cannot do that. So there's no pathwise definition on an integral that is continuous and on a space that is large enough so that you can define the Brownian motion on it. In other words, there is no generalization of the Young integral. You can, whatever topology you choose, no generalization of the Young integral you can use to integrate two Brownian motions, or the path of two Brownian motions. So let's look at the proof, which is surprisingly easy. So we define two processes here, Wn and W tilde n. So n is fixed. And you take just a truncated series as before. Okay. And what is important here is that in both definitions, we take the same Sn and Cn, so the same normal random variables. So they're not independent or anything. No? So this is important here. So these processes are correlated. They agree in distribution because, minus a normal standard normal random variable is in distribution equal to plus the standard normal random variable. Yeah. So they equal here. And by assumption, both of them converge almost surely to a process W and W tilde. That are then also equal in law, of course. Yeah, so let's assume, so by contradiction, that we have a bilinear map satisfying the stated conditions. Well, then we have, since it's continuous, then we have that also these quantities here should converge almost surely as n to infinity, yeah, by continuity. But now you can really calculate this one here. So IW, WN, IWN tilde, what was it? But that one here, and yeah, okay. So it's just that, right? Because we assumed that both so that this map agrees on the trigonometric agrees to this integral on the trigonometric functions here. But now if you write it down, so if you have dw here, of course you can, they are all differentiable. So for a finite sum, you have smooth functions here, all the trigonometric functions. So they're differentiable. You can put the differential here inside, and then you integrate. But then you use that the trigonometric functions are a basis, an orthonormal basis in this L201 space here. So a lot of things will cancel. I advise you to do this calculation if you want. So a lot of things will cancel, and it's chosen here exactly in that way that what remains here is this sum here, and here you square the normal random variables. Square the normal random variables. But now, when you have squared normal random variables, of course, there's no cancellation going on there anymore. So there's no, they're all non-negative, these random variables. And now you have a series, you want to pass to the limit here, so n to infinity, but then you have something like the harmonic series, and this, this will diverge, which is then the contradiction. Okay. So you can ask now, well, doesn't that contradict with what I learned in stochastic calculus? Because we saw that the WNs, they converge to a Brownian motion plus something smooth, yeah? So why can't I define this integral here? Because it's just a Brownian motion plus something smooth. But in fact, it's not a contradiction, because you want to integrate two Brownian motions here with respect to the other, but these Brownian motions are highly correlated by construction. So none of them is adapted to the filtration of the other. So the Ito theory does not apply here. Nor does the Stratonovich theory. So it's not a contradiction. Okay. Okay, so this was this meta theorem which somehow told you, okay, you have to find another solution. Yeah? So you cannot just look for another integral, it will not work. Okay, so this is the goal of this lecture, if you want. So we would like to solve an equation of this form here, pathwise. So say for x being a Brownian motion, or actually any, so possibly rough signal x, or now we come back here and say x is just a path. Yeah, so we will not look at the probabilistic. So we forget about probability for the moment. So here x is really just a path, not a stochastic process. So we'd like to understand a good notion of a solution to this kind of equation. Well, we can try to be a bit, less demanding. So we can, often it's good to look at easy equations first. And a more easy one would be a linear equation. So we can look at this equation. So the sigma here, maybe in one dimension only, would just be the identity here. But still, what we would like to do is we would like to have here several drivers. So D driving signals. This kind of, we can now, again, an ordinary differential equation. This kind of ordinary differential equation, when you try a bit around, maybe come up with an idea what the solution could be. So you start to expand this solution. Taylor expand the solution, or you think, okay, let's assume that it's smooth. What kind of expansion can I expect? And then you realize that this is maybe a way to write down a solution to this equation. And it indeed is in the smooth case. So if you can define the iterated integrals here, so if x are all smooth paths here, this would really be a way to write down the solution to this equation. Okay. At least we found an expansion, but well, of course, there's a problem here because we just learned that there's not a good notion of an integral we can use if we want to integrate xi and xj with respect to the other. But the idea of rough path is somehow that you say, okay, let's just assume I have them. Let's assume that I have an iterated integral, and let's see what I get with it. Maybe I obtain a good notion of what an iterated integral should be. Maybe there are some examples where I have somehow have a good idea what this should be, even if I cannot make sense of it as a Riemann sum. But then you will ask, okay, but an iterated integral, what actually is it? I mean, if I cannot define it as the limit of a Riemann sum, what is an abstract definition of an iterated integral? So what are properties every iterated integral should satisfy? Okay, and so let's look at the example of a second iterated integral here. Now, so let's assume x is smooth here. So it has, D components, and end, all the integrals would can be understood as an element in the nth tensor power of RG. Like the second can be understood as the second tensor power of the fifth power, and it can be understood as integrals. So the selection of all iterated integrals, now all together, would then be an element in the direct product of all these tensor products. Okay? And so we introduce this direct product, so we define it. So, and this is this symbol here, called the extended tensor. You put the direct product. For technical reasons, you don't start with RG, but you start with R, which is then the zero tensor. And this we give the name, and this is the extended tensor. And the first tensor power here also is RG. So this is the space. Again, why do I introduce the space? Why do I have a look at the space now? Because this is the space where all these iterated integrals can actually live. Where you can store them in the smooth. And then we define projection maps. I will read them later on also. So the projection maps of the nth tensor power. Okay, what is this object here? What do you know about that? Well, first of all, it has a linear structure. It's a linear structure because all these here are linear spaces. You can also divide the product with a linear space. So note that I do not put any norm in. Okay. So just view that here as linear spaces. So they are linear spaces, but I can also define a product on it. You can define a product on it, and this product is defined like that. Right? The product here and here, it's like that in the literature, so I don't want to change it now anymore. But it's the same symbol as you use for the tensor product. So here I use the symbol, so that these are the same symbols, but in one case, namely on the left-hand side, I define a product, where on the right-hand side, I use the tensor product, for elements of RG, or tensor product. Okay. So how is this element defined? Well, I can define it by saying what it should be on any level. So on the nth level, it should be just the sum of these elements here. These are where the projections on the E tensor power of RG, these are projected in the J tensor power of RG, and if the I plus J sums up to n, then this is actually really an element in the nth tensor power of RG. So this is finite sum algebra. That's the end. So if it all combinations here, this sum actually runs over IJ. From 0 and IJ runs from 0 up and down. So then we define, it turns out to be a unit element, and that's why we have to introduce, so that's why we started not with ID, but with R in the beginning, because here the first conformity is really the number 1 in the real numbers. And the rest are then the 0 vectors. Okay, and this turns out then to be really a product. So it's distributed and behaves nicely with a scalar product. So in total, this thing then is not only a linear space, but becomes an algebra. So since this product here is associative, it's an associative algebra, and the one here is really the unit element for this multiplication. So this is an associative unitary algebra with this product. Where you can also just do, if you want, the calculations. Okay. So given now a path, a smooth one, we define now a lift of this path. And the lift of these paths are exactly all its iterated integrals. Yeah? So what is this lift? So this lift is an element, is a map here from the simplex. This is just the simplex to the extended tensor. So what are all the levels? Well, on any level here, the elements here are the iterated integrals. Which is just the definition. And this is, I can do it because the x here is, remember, it's really small. And here, just to remind you, these were just the collection of all iterated integrals. You can think of I1, I1, range 2, range 2. So this is true for n. For instance, for n equal to 1, for n equal to 1, you would get here the increments of the path, not the path. And on 0, you just define this element to be 1. So the lift of x is therefore just a collection of all iterated integrals seen as a map with values in the extended tensor algebra. And then you have this very nice theorem I will unfortunately not prove, which is somehow the generalization of this calculation I performed for the second level. So it tells you the following: if you have a smooth path and you look at the canonical lifts, so you look at all iterated integrals, and then you take three numbers S, U, and T, and then this as an element in the tensor algebra equals the element SU product element with T. Every SU. Okay, this is a very nice form. It looks very, very beautiful, I would say. So, and indeed, now let's go back to our calculation. Let's convince ourselves that it's really a generalization of what we calculated by hand. So from Jen's theorem, we know, first of all, okay, so this is the, I don't know if this is the second level here. I used the same notation. I should have put brackets. Not, I should have taken brackets here. So if this is the second, so here's on the second level, so I can replace this here by the projection of the whole path of the bold x as t. But this is a step I didn't write down here. So this is pi 2 of bold x as t, and then I use the Chen relation. So then I'm here. So the identity of Chen's theorem, which is called sometimes Chen relation. So this is that one, and now you just use the definition of this product, because here you have the projection. So let's go back. So you use just that one. The definition of this projection. So this is the second level. Yeah. So this is the second level of that one here. You tensor it with the 0th level, but the 0th level was by definition just 1. So you just, and this is, you don't have to write down then, because tensor 1 is then just this element. Here you have the second level of this element here, tensor. So then you have the 0 tensor in the first, from the left, which you can also ignore. And then you have the first level here of this one tensor, the first level here. And because 1 plus 1 is 2. So this is that one. And this is exactly what we calculated before. So what you see here is, at least on level 2, the Chen theorem just encodes this elementary property that an integral somehow is additive in that way what I found. And you can now, if you want, do also the thing on the third level and the fourth, and you will see the same, that it's really, this is the property what really encodes this linearity of integrals, the chain relation. Okay, now we define, so we can look at the whole tensor algebra, which is then of course infinite dimension. It's an infinite dimensional vector space. Yeah? We can also look at the truncation somehow. So you can fix an upper level here, say capital N, and then look at the direct product of the first n. Here's a typo, sorry, here should be a capital N at the very end. Okay. Capital N. And this then would be a finite dimension space. First of all. Okay. And so it's when I write direct product, then I can also write direct sum. This is called the truncated tensor algebra at level n. And truncated tensor algebra inherits all the structure, so inherits the product we defined before, and you can also define the corresponding one element here. So also the truncated tensor algebra is then really an algebra, associative unitary algebra, as before. So when we fix an element, now we take we do an abstract definition. Huh? Before we said, okay, we define a natural lift both x, and then we deduced the chain relation. Now we go the other way around. Now we say, take any element satisfying the chain relation. Any element that satisfies this chain relation here, we call a multiplicative function. Yeah. So in particular, the canonical lift of a smooth path would be, or if I truncate it somewhere, would be a multiplicative function. So this would be an example. So what do we know? So for now, I'm quite quick today, so I might finish earlier, but I think it's still a lot of content, so we have not time for questions maybe. So what do we know about multiplicative functions? Well, they somehow satisfy an algebraic property, namely this additivity of an integral. Yeah? So this will be one characterization of what an iterated integral should be. And there's also another property iterated integrals will satisfy, and this will be an analytic property. And this is something we want to have a look at now. So what is the analytic property? So let's go back to the Young integral. So for an alpha Hölder path with an alpha Hölder index larger than 1, we knew something about the difference of, so about, we know something about the increment here. We know that this is a big O of t minus s. So you can write the difference, the increment here also in iterated integrals, and you realize that this is a big O of t minus s to the alpha. Okay, so this is just a definition, if you want, of what is an alpha Hölder path. Yeah? So what about the second iterated integral? So the second iterated integral you can rewrite like that. So it's that one here. And then we had an estimate, if you remember last time in our theorem, we had an estimate for this kind of integrals. And the estimate told us that this is actually a big O of t minus s to the 2 alpha. So what about higher order iterated integrals now? Well, first of all, in this particular regime here, you can define them. It's not a problem, because when you fix here the s and let's look this as a path in t only, then you can show, follows from this calculations here actually, that they are alpha Hölder continuous. So you can go on if you want. So iterated integrals are first of all really defined as Riemann sums as you would as you expect them. But we don't know yet about their regularity. And this is something we try to find out now. And so we will use our skewing lemma. So what I do now is a bit surprising. So you could say falls from heaven. So we make an ansatz here, which turns out to be very also know here minus psi st. What was psi st? This was the sum of these two elements here. This was psi st. Okay, so what can I do now? Well, first of all, I can put this element here inside the integral because the s here does not depend on u. So here I have something which does not depend on u. So this is exactly that. Okay. Here I don't do anything. Okay, in the next step, I use again for this term, for both, I use the Chen relation. So I have the x as u2, and then the tensor power of the increments. Here again, I don't do anything. But now, okay, now what happens now is and so let me try. Okay, so first of all, okay, so you can integrate this one here. This is fine. Oh yeah, okay, now I see it. And then, okay, so this term together with this term is exactly this. Okay? So what is happening here? So here you should realize that this, first of all, this increment does not depend on you. So you can take it outside. You can take it outside. So then what remains is an integral sd delta x su dxu. Yeah. But this is then nothing than this term here. So then this integral here, what remains, is equal to this term. It's equal to this term. And this here you put outside, and then realize that what remains is answers. What remains is exactly that one here, and this is the iterative result. And what we did now with the Turing lemma is that we deduced the regularity of the third equation. Namely, how you could have guessed, really the big O of t minus s to the 3 are. Okay, this kind of long calculation now can be really generalized, and we can generalize these arguments, and we can show that for the alpha Hölder part, large alpha, you can actually look at the n correct integral, and this kind of induction argument. You see that the regularity is actually really n for everything. So this is what also now gives you an idea what is the analytic property in iterated integration. So let's go back and let's have a look what we actually used to deduce that. We used only two properties, namely we used Chen's relation, and only for the first and the second level. And we used the alpha and the 2 alpha Hölder regularity of the increments, the first level and the second. So this is all. That's all. And in the Turing lemma, to apply the Turing lemma, what we actually needed was that 3 alpha was larger than 1. This is what we calculated. So what we had was way more. We had that alpha for us was larger than 1/2. So this was in particular true. But now you can think of, well, if I had an object here, delta x and x2, satisfying these two conditions, so the Chen relation and this analytic condition, only for an alpha larger than 1/3, we could have done the same. of x that agree up to some level n larger or equal to n. So we will do an induction proof. Yeah. So we assume that they already agree, and then we will prove it now that they will agree on level n plus 1 as well. Okay. So we look at the n plus 1th level here, and we look at the difference. Okay, so, and now we use the Chen identity, first of all. So this was the same trick as before. So when I'm here on the nth plus 1th level, I can also look at the projection on the n plus 1th level of this object. And then I have these two things here, use linearity. And here I use the Chen relation then inside. So in the next step, I use the definitions. I use the definition of this product. But then here I have a minus, and then so there will many terms here will involve the lower levels. Many terms here will involve the lower levels. So levels, almost all terms will be on level n or below. And there we already assumed that these two extensions agree on these levels. So actually a lot of cancellations will go on between this, and the only thing what remains here is the n plus 1th level, here and here. So here you use the definition again of the product. Okay, but then you see, well, this was just the definition I did before. So this is psi SU and this is psi UT here. Okay, so, and from this identity here, it follows that if I look at this path here, then the increment of this path here, so the path is now 0t, is exactly, so if I look at the increment xt minus psi t minus psi s, this would be the increment, this would be equal to psi st. And psi st, we know is n plus 1 alpha Hölder regular. Yeah? Because this is also this was a property of this extension, right? So, but now we are really in this situation that we have a path that has n plus 1 Hölder regularity. And this by assumption is larger than 1. So we know that psi, this path here, is actually constant. So the increment here, which is just psi st, is 0 for every s less than t. So this shows then that these objects are really the same. So this shows uniqueness. Okay. So this was the extension theorem, and there is a nice, so you can work a bit more. So we did not do the existence proof, but when you work more on the existence proof, it is possible to show even, to say something about the norm here in terms of n. So remember that the norm, so these elements here were just the nth order iterated integrals. So, well, for the when you look at iterated integrals, it's the same. Well, you know that from analysis maybe or calculus, you can define the nth Riemann or the back iterated integral, just integrating the number 1. So this is the same as integrating over the nth simplex. And the volume of the nth simplex, or 0, from 0 to 1, would be 1 over n, power n, 1 over power n. So you know that these iterated integrals decay factorially fast. And it's natural, or it's not so surprising maybe that something like that happens here as well. So the nth iterated integral, then even the norm, the alpha Hölder norm, they decay at least faster than exponential as n tends to infinity. But to deduce that, you have to work more. So it's a bit harder. And you need a certain inequality, which is also not at all trivial. A proof for this you find in Lyon's lecture notes. I'll give you the references at the end, if you're interested. And what do I need? you can also be more precise, saying what is faster than exponential? Well, it's a big O of 1 over n alpha, power n alpha. And by this, I mean, this is the gamma function, or gamma n alpha plus 1. So, and you see in particular that for a lower regularity here, this convergence to 0 gets a bit slower, but still it's quite fast. Well, it's still faster than exponential for any alpha. Okay. Okay, so now comes really the definition of a rough path. Now, of a alpha-Herder rough path. So what is an alpha-Herder rough path? Well, it's a multiplicative functional, first of all, so it should satisfy this usual additivity. And it has a certain regularity, namely the alpha regularity. And up to that level, so we assume that up to a certain level, from which on you can use the extension theorem to get also the higher order iterated integrals. So you define a rough path only up to this level, because the rest you get for free from the extension theorem. So rough path is an element only, fortunately, one has to say, only in this finite, takes values only in this finite dimensional space and not in the full, in the extended tensor algebra, which would be an infinite dimensional space. Yeah. So, and this, this condition here is exactly the condition that tells, okay, from this level on, I can use the extension theorem to get also the rest of the iterated integrals. So this is an alpha-Herder rough path. So it has this algebraic and this analytic. So it mimics iterated integrals, and it mimics the algebraic and the analytic properties I talked about here. So then some notation, we will denote the set. So first of all, it's a set of Herder rough path by this curly C here, or sometimes only, so sometimes I put also 0t RD, sometimes not, if it's clear from the context. And we also define a natural extension to a rough path, which was the one, so you can ask, of course, yeah, but what are rough paths? I mean, are there any? Is the set, isn't it empty? But we already know one. Namely, we know that if I take a smooth path, if I take a smooth path and I look at the of the natural lift, then this gives me a rough path. Okay. And in general, so this definition here, if I have any alpha-Herder path, and X is any rough path such that the first level coincides with the increment here of this, then we call X a rough path lift of X. Just by definition. So first, there's of course two questions now. First is, can I, for any given Herder path, can I define a rough path? Of course, can I define a rough path lift? And second question would be, is this lift unique? We will not be concerned with this, so I will not solve this question, these questions here. I will not prove the answers to these questions, but I will tell you the answer. So first answer to the question of existence is yes. So for any given Herder path, there is indeed an extension to a rough path. But the second question, and this is maybe not so surprising if you think about it, is no. So it's not unique. So you can have for any Herder path, you can have an extension, but yeah, it's not unique. It's like that. Well, in certain cases it is. If the path is smooth enough, for example, you know already that there is a unique extension from Lion's extension theorem, and then it's unique. But when you have a genuine rough path, then it's not. Okay, so now we are already in the position that we can give a meaning to the solution of a linear rough differential equation. Because remember, at least in this example in the beginning, we just wrote down a series expansion of the solution, or we wrote down a formal series expansion. And now, in this series expansion involved these iterated integrals. We could not define, but now we can say, okay, if I have a rough path, I have all these iterated integrals. So I just define my solution with the help of the series expansion. And we can be even more general. So in the example I showed you, it was really a very easy equation. We can look at more interesting equations. Namely, we can have just any linear function here, linear a's, applied to yt. And okay, so here it gets maybe a bit tedious. So what is exactly a linear function? How should I, how do I define that here in coordinates? So this I suggest you that you maybe have a look on it yourself. So it's really a generalization of this example I gave you in the beginning. So this, we aim to solve this equation here where A can be either seen as a linear map applied to Y or as a linear map applied to dxt, depends a bit how you want to understand it. And a natural candidate, when you think about of a solution to this here, would be an expansion, would be this infinite series here, involving then these powers of A. And here are the iterated integrals. And here I use the symbol of iterated integrals, but what actually mean here are the elements of this rough path X here. But I still use this one here because it's very suggestive. In one way, it's good to write iterated integrals because somehow you know what I mean, but you should always keep in mind that they are usually not defined as Riemann sums, but they are just the elements here in this, of this rough path. Okay, and there also what I need here, well, when I write infinite sum, what I implicitly use here, that I really have all the iterated integrals, and not only the first n, but I have all of them. But this is fine also because due to Lyon's extension theorem, when I have a rough path, I also have any iterated integral you can think of. Okay. So this is a bit more notation. What is the a to the power tensor n? So this is exactly that one. The Euclidean base, so it's a linear map, x blah, blah, blah. As I said, maybe you should do that on yourself. But as an example, we can really think of this example before. So if all of these matrices are the identity matrix, then this series expansion would be exactly the one I wrote down here in the beginning of this lecture today. And again, I use this notation here. So this is then this element, the nth element, and then I use these coordinates here. But if the path happens to be smooth, that are really the iterated integrals. Yeah? And what I also need here is, well, now you can ask, of course, what's about the convergence? Do I really know that this series converges? And the answer here is yes, if you have the strong form of the extension theorem. So the strong form would mean that you also know that these iterated integrals, the nth order, decay faster than exponential, because then you can really prove that this series converges absolutely to something. Okay, so we are there. So we defined rough path, and we saw that having rough paths, so in other words, having all iterated integrals, are actually enough to solve linear equations. I mean, I didn't give you really a precise definition, but this is, I would say, a good candidate of a solution. I mean, a reasonable candidate because it's really extending also the classic, so the case in which the driving path happens to be smooth. So now let's look at the Brownian motion. Yeah. So in the former section, everything was deterministic, so no stochastics coming. Now, yeah. So our goal. Usually, why do we do all these theories? Because we want to apply it in stochastics. So we can solve already linear rough differential equations. Can we now solve linear SDEs? And well, this would be possible, but what we need is then somehow a lift of the Brownian motion. Yeah? Because the Brownian motion is, well, we defined it, or you define it in stochastic calculus, but what we did not define is an iterated integral. Yeah? So what we need is somehow a natural extension of the Brownian motion to a rough path value process, whatever natural means. Okay, so let's take a Brownian motion, a d-dimensional Brownian motion. We will take independent Brownian motions as usual. And we know that their trajectories have a certain regularity, namely they are alpha Hölder for an alpha arbitrary close to 1/2. Yeah? Okay, so that means when you think of the definition of a rough path, the condition there was that, okay, well, yeah, you can see that what you actually have to define a rough path here, we only have to say what the second iterated integral should be, because we can be arbitrary close to 1/2, okay? Smooth enough. Okay, and for the second iterated integral, now, and this is something which is where stochastics coming in, because stochastics now gives you natural candidates. So if we did only analysis up to now, well, I told you that there's a theorem telling you that you have rough path extensions, but there are infinitely many. So you don't know what is a good candidate. But for stochastics, there are good candidates. So, and one is the Ito integral. So we could define this iterated integral here with the help of Ito. So then our rough path here would be first the 1, okay, then the Brownian motion, and then the Ito integral. But there's also another notion of what a good integral could be, and this is the Stratonovich integral. So we also define that. So the rough path lift of the Brownian motion in Stratonovich sense would be, so the second level would be that one here. You can rewrite that also with the help of Ito. There's an Ito-Stratonovich correction. You will learn that, I think, in stochastic calculus. So, yeah. So where the integral is understood, yeah. In the middle integral here is the Stratonovich integral. So these are two candidates. They are candidates because we still have to prove that they are really a rough path. Yeah. So this is not immediate. They are stochastic integrals, but do they really satisfy the conditions we wanted them to satisfy? And we wanted them to satisfy almost surely, of course. So both Ito and Stratonovich satisfy this rule here. It's quite basic rule. So they will also satisfy chance relation. So that means that these processes I just defined are multiplicative functionals almost surely. Yeah. But what we do not know yet is what is their regularity. Yeah. So the regularity is still not so clear to us. And okay, remember how did we check the regularity of a certain stochastic process? In the first lecture, we used the Kolmogorov-Chentzov theorem for a stochastic process. And fortunately, there is an extension of this theorem now also to multiplicative functionals. And this is the Kolmogorov-Chentzov theorem for multiplicative functionals. Yeah, so we formulated here also for only for level 2 because, well, this is where we use it. There's also a formulation for higher levels if you want. So we have to have two properties have to be satisfied. So when you look at the Kolmogorov-Chentzov theorem, we only had this. There was only this condition here, but now we also need a condition on the second level. On the second level here, we have the AQ norm, the AQ omega, and here we have AQ half omega. So these are two conditions. On the norm, or on the moments of these stochastic processes, random variables, if you want. And then the conclusion is the same. So for the first level, it's really the same. So for any alpha smaller than this thing here, I can bound this here with a random variable k alpha, which has finite qth moments, and also the second level I can bound here by a random variable which has finite q half moments. Here I have the 2 alpha, and since they have finite moments, they are smaller than infinity almost surely. So in particular, the norm here of this multiplicative, the alpha norm of this multiplicative functional is finite almost surely. Yeah, so this is an extension of the usual Kolmogorov-Chenchov theorem. You can also do it yourself, try to prove it yourself as an exercise, because it's almost the same proof. If you do not want to, you can look at Fritz Heirer's book. They will do that also there. But the corollary is then, as before, that the E2 and the Stratonovich rough path lift have a regularity of alpha smaller than 1/2 for every alpha arbitrarily close to 1/2. And well, I'm here quite quick, I have to say. Maybe you will talk a bit more about that in the exercise sessions. So there is a thing which is Brownian scaling, and this Brownian scaling will tell you that indeed these conditions here will hold for beta to 1/2, for beta equal to 1/2. Let's go back here. Yeah. So here I have beta, yeah, and the second order object then scales not like 1/2, but like 1. So then you have a 2 here, and so it's a 1. Yeah. The thing which is a bit delicate maybe is, okay, using the E2 isometry you will learn about in the stochastic calculus course, so it's easy to deduce that for q equal to 2, then this is immediate, but to deduce that at least for the second iterated integral to any q is a bit, maybe a bit more complicated, but believe me, it's true. Believe me, it's true. So from this corollary, we know now that E2 and Stratonovich rough path lifts are both rough path valued stochastic processes, so you can use them to solve linear stochastic differential equations driven by Brownian motion. So now you can ask, okay, but what in practice, what should I take? Which one is the right one? Should I use the E2 or should I use the Stratonovich lift? Both we saw are possible. But in fact, this question is not a meaningful question, because it will depend on the problem. It will depend on the problem you want to model. Maybe we'll talk about that also in stochastic calculus when you introduce E2 and Stratonovich. So E2, for example, is often used in finance because the solution of an SDE, of an E2 SDE, is a martingale or semi-martingale, and this is what is reasonable in finance. Stratonovich can also be useful in other contexts. We will see why Stratonovich is maybe also a very natural choice. But the message here is there's no correct rough path. So it really depends on the equation, it depends on the model, it depends on the problem. And this will determine which rough path you have to use. Okay, so I'm done with the lecture. Almost exactly on time. So what I talked about today mainly has, so there are 2 sources. So there are these lecture notes from Terry Lyne, still very nice, I would say, although they're now quite a bit older, from 2007. So this linear equation, solving this linear equations was exactly done there. And of course, this is my main source here, the book from Peter and Martin. It's a bit more modern approach, but has also some disadvantages, some here and there, I would say. So I think both are very good sources if you want to learn about the topics of today. Okay, thank you very much.
So we will take some questions now. Any questions on any of the proofs? No, everything was 100% clear, I think.
Well, actually, there are really many. There are a continuum of extensions somehow. But on the so you can somehow say what two lifts, but I have to look it up. I think what two lifts should both satisfy. But still, there's a continuum of things what you can think of. So, I mean, so for example, I mean, it really depends on the model. So maybe you know the Wong-Sakai theorem for stochastic differential equations. So somehow this is a discrete approximation. So no, it can be seen as a discrete model where you want to pass to the limit somehow, and you want to consider the continuous model. And but this models, I mean, for the Wong-Sakai theorem, you approximate your noise in a certain way. Yeah? So there's for example, you can approximate the noise at some points piecewise linear, and or you can approximate it also with I don't know, taking convolutions or anything. And these approximations, they will all converge to the Stratonovich solution of the equation. But it was known also for a long time that there are also kind of approximations which are not so natural. So where maybe the Brownian, so you can approximate the Brownian motion in a different way, and in the uniform topology, these approximations will also converge to the Brownian motion, but the solutions of the stochastic integral will not converge to the Stratonovich solution. And yeah, and with rough path, you can understand what's going on, because then the rough path will not be the Stratonovich rough path, but will be another rough path. And yeah, so this is yeah what often happens. So, I mean, it's a question, how do you see an SDE? I would say an SDE, a stochastic differential equation, is somehow an idealization of a discrete, often an idealization of a discrete model, but we have to understand the discrete model to properly define what is then the limit somehow, what is the good approximation.
Thank you. Any other questions? Yes, please.
So at the end, we showed that the Brownian motion is indeed a rough path.
Okay, so what I showed is that a Brownian motion, so an RD valued process, has somehow a natural extension to a process you call a lift to the Brownian motion. And there are actually two. So at least I talked about only two. Yeah.
Yeah. So I don't think it was clear, but does it mean that then the solution of stochastic differential equation coincide with a rough path solution?
This we did not show.
But does it usually coincide? Is it immediate?
Yes, it's not immediate, I would say. At least I don't know an immediate proof. But we come back to that question. But I used these terms Ito, Stratonovich, not only because I used the Ito integral to define them, but what is true also is that the Ito solution driven by the Ito rough path will be the same in law to the Ito, so the solution of an SDE where you interpret the solution as a solution to stochastic differential equation with the Ito integral. So they will be the same, yeah. And Stratonovich as well. But it's not so, I would say it's not so immediate to see that. Yeah.
Okay, thank you.
Okay, I'm not too sure if we have time for a potentially final question. Oh. Okay, so if nobody has any further questions, I think that closes the talk.
Okay, thank you.
Hola, hola.
Ya. Tú me dices cuando lleve como cerro, porque tengo, no son tantas, ¿ah? No son tantas.
Estás empezando más tarde, te aviso.
Ya.
Vas a empezar y eran 55 minutos. No, perdón, eran
40
45.
minutos.
Ajá.
Avísame cuando sean las 16:35, me enseña.
Cuando faltan 10 minutos.
Sí, sí.
36, 35 te digo. Alguna serie. 35 más.
35.
35, dale.
Entonces ahí voy a saber dónde estoy.
De las speaker, profesor Soledad Torres, from University of Valparaíso. She talked about forward integration of boundary variation coefficients with respect to the Holder continuous process. Can you start?
¿Se escucha? Sí. Okay, thanks, Christian, and thanks for the invitation for the organizers. It's a pleasure to be here again and again and again. My talk is about forward integration of boundary variation coefficients with respect to Holder continuous process. So maybe I will ask later to Sebastian about Bruce paths here for a kind of non-ellipses or not regular kind of coefficients. Let's start with the introduction of my talk. Okay, so what was the motivation of this work? Some years ago, we were trying to understand in the fractional Brownian motion what happened in the case that the coefficients, the diffusion coefficients, are not anymore ellipses or had a linear growth. But especially if you have coefficients, sigma, that are discontinuous or have discontinuity points. So in this case, there is an old paper in the 70s, in the case of Brownian motion, that say that in a general way, you can ensure pathwise uniqueness for this equation, okay? So our question was, what happened in the case when the coefficients are not nice or not regular enough, and what happened if we change Brownian motion by fractional Brownian motion? Okay. So, like an example, consider this equation. It's a very simple equation. When the coefficient is a constant when x is greater than 0, plus a constant when x is less than 0. You will say, what? You consider these coefficients? Well, you will see a little bit later. But it's only something like this, very simple case. So both positive, and this is sigma. Okay. So simple, but in order to prove the existence and uniqueness for this equation, it was not so easy to get it. But again, why in our motivation for this work, we use this coefficient, diffusion coefficient with discontinuities? Because in the Brownian motion case, after this function of the process, the solution of the process, and Tanaka formula, we get the well-known skew Brownian motion. Okay, so at that time, we was interested in what happened if we change Brownian motion by fractional Brownian motion. And in this way, it's an open problem until now. Okay. Okay, so this was our motivation. And in 2017, we prove in the case of fractional Brownian motion, even more, but in the case of fractional Brownian motion, we prove the existence and uniqueness for the solution. But we were not able to prove that we have, of course, this relation, because Ito's formula, and as Sebastian said today, Ito's integral works for Brownian motion, especially in the case h equal to 1.5. Okay, but even that, we start to think about this equation with sigma is not regular enough. Other example that we will see later is the case when sigma is the sign. We know that in the case of Brownian motion, exists, the solution is in law and it's a Brownian motion again. Okay, we will see what happened in the forward case, what is the kind of representation, if we can get it a representation. Okay. So in the case of sigma like this, and of course a little bit more general kind of discontinuity, we prove with Jorge León and Joana Garzón. Jorge León from Simvestab in Mexico, and Joana Garzón from Universidad Nacional de Colombia in Bogotá. We prove that if we have the Lamperti transform, after a while, we can get the solution and the uniqueness for the equation with fractional Brownian motion. Okay, but this is only our motivation for the work that I want to present today. Okay. So sigma now it's a more general kind of diffusion or coefficients in our stochastic differential equation. And why think in fractional Brownian motion, but think again in Holder process, Holder continuous process. Okay. Okay, so at that time, what kind of integral we use in order to prove existence and uniqueness for this simple equation? We use the generalized Stieltjes integral. No Ruspas, sorry. It will be nice to prove the same kind of results if we work with Ruspas, but I really don't know how to do it. And it will be interesting to try to get a basic result using the techniques of Ruspas, because there are a really nice technique to do it. So we just analyze the Stieltjes integral, who is more or less given by the fractional integrals of order alpha. And just to say some words about that, because we are not going to work with generalized Stieltjes integrals, even that we are going to work with forward integral. Sorry again, but maybe next year we will work with Ruspas in this kind of thematic. Okay, so this is the definition of the generalized Stieltjes integral. There is a introduced by Saleh, essentially. So we work in this case with that problem. Okay, so again, in our mind was trying to get existence and or uniqueness for a general class of diffusion process in our SDE. And try to get some result concerning to sticky Brownian motion related with the fractional Brownian motion, the integral with the sign, and the equation with discontinuous coefficient, or as we notice, singular coefficients. Okay? Okay. So again, the definition is just to say that you can work by hand using this generalized Stiglitz integral. After a time, you can do a lot of calculus computation, but it's not easy, but you can get it some nice results. Okay, so this is the fractional derivative that we produce in the fractional calculus, etc. So the main thing is that you handle with two integrals that is more or less given by this term, okay? But even that, okay, it's okay. What happened after that? There was a paper by Chen and Laurie, and I forget the third name. What he said, using generalized Stiglitz integral, they prove that he has a representation, or he has a formula for a function f, in our sigma, that is locally finite variation with derivative, and y, thinking our fractional Brownian motion, alpha Holder continuous process with alpha greater than 1.5. Okay. So what was the condition for y? Is that has a density which satisfies these two conditions. Okay, so you think in fractional Brownian motion, the density of the fractional Brownian motion satisfies this condition. Okay. Okay. So what we think, okay, what the next step is to use other kind of integration, and that we use is the forward integral. Okay. And what is the forward integral? So we have generalized Stiglitz integral, forward integral. So you can go in some direction using what you need or what you want to prove. In this case, the forward integral is defined in the sense of Rousseau-Valois, is defined by this limit in probability. Okay, so it's ys plus epsilon minus ys, and then is ds here, and 1 over epsilon. So this is the integral that we will use in the rest of this talk. Okay, so x and y are processed with some nice conditions, continuous path, etc. And we want to know what is the concept of this integral, that we use the notation, the usual notation, xs dy minus s. Okay? Okay. Okay. So there is something that is really nice, that is the definition of the quadratic variation of a process y, who is the limit in probability of this integral. And what is interesting here, that Rousseau-Valois proved that if the existence of, if the quadratic variation exists, then you have this formula. Okay, it's more or less the Ito's formula. But if y is alpha Holder continuous and alpha is greater than 1/2, then the quadratic variation of y is equal to 0. So this term disappears. So if we work with y alpha Holder continuous with alpha greater than 1/2, we will think that we have, of course, this formula for the representation for f in yt. Okay, but f is very regular, very nice, in order to ensure that, for example, the existence of the second derivative, etc. So our question was, what happened? Remember that Chen proved that they have the same, this theorem, but when he used, or they use the generalized stilted integral. So our question was, of course, what happened if we use the forward integral? And the answer was, okay, we have the same kind of theorem. But remember that this integral is in probability. The limit is in probability. So the way to prove that this formula is correct with this kind of integration is completely different, okay? Because generalized stilted integral, you have to compute all of this integral with the derivative, etc., by hand. But here you have to get a limit in probability because the integration is with the forward integral, okay? So if you change the kind of integration, of course, you have to change the kind of proof. Okay, so let's start with, I hope, a simple sketch of the proof, okay? And you will see what is really different in somehow, because we will use only a kind of probability stuff. Okay, so some definitions. So the kernel, the Gaussian kernel, then this definition in order to get more or less a view of what is we are trying to prove finally. Okay. So this is f is the integral of f prime. F prime is the integral of f times this kernel, and yt epsilon is somehow is an approximation of the process y, who is the alpha Holder continuous process. Okay, so keep in mind not all the definition, but remember that f is linked by f prime with the integral, and f prime is given by this f, and this f is what you have in the SDE, or thinking f in the SDE. Okay. So what is the idea of the proof? We will prove that this limit is equal, this integral is equal to all of this, okay? Why? Because, of course, we try to prove directly, but nothing happened directly. So we have to pass for these steps. Not all of the steps was by one, but you will see. Okay, so, and remember that f prime was defined by the integral of f p epsilon s. And f, and this is the result that we want to prove. Okay, so first, we prove this quantity just in some step. So here again, the kind of the proof, as you see, we do use the notion of integration, okay? It's a little bit different, the concept and the step that we want to give in order to prove our results, okay? So we were, by hand, we prove first that these two terms are exactly equal, okay? So, okay, so using the mean value theorem, then some bounds of this quantity is exponential, a lot of algebraic inequalities, then we are be able to prove that f prime in x minus f prime in y is less or equal to this quantity, okay? So that I said that everything was doing by trying to get the best bounded, the best bound of the quantity that we are trying to use. So after that, we prove exactly that we want. So this is an equality for each epsilon. There is no limit, but anyway, remember that. So we have this is equal to this. Okay, perfect. But then, since I said firstly that we weren't able to prove that directly that this one, this is like essentially this integral, we need to pass for these terms. So the second part is that this limit, now in the limit, in LP, converged to this quantity. That is the last quantity we want to prove. Okay, we didn't use these terms. Okay, so there is other lemma in order to prove that. Okay. Okay, again, some inequalities. Well, very easy. This is the easy part to transform this quantity in 4 terms. Okay, so the first ones related to f prime and f here. So we have to pass by our kernel P. The same here. And here we have yt epsilon, that is an extra problem. And those are more or less the same as y1 and y3 are more or less the same because it's from y0. And these 2 parts more or less the same. So we need to handle y1 and y2. So, okay. Okay. So first, y2 is just less or equal to the difference, a constant by the difference of yt epsilon minus yt. And then you can prove that yt epsilon, remember that is 1 over epsilon, the integral of y t minus t infimum t. You can prove that, let me show you what is y epsilon. So it's here. So you can prove directly that this is yt epsilon minus yt is less or equal to epsilon to a power. Okay, and the power is the same as the Holder continuity in the case for the process y. Okay, so this is y2, so essentially this part is okay. So then the second part is a little bit more work because f, we assume that f is absolutely continuous and have a measure μf. And then we need to work with, especially with the Gaussian kernel. And a lot of inequality of the Gaussian kernel, we're trying to observe or to get it or to found in order to get our inequality or prove that y1 goes to 0. Okay, so again, we prove that this is equal to this, and this limit is equal to this one. So rest to prove that this quantity is equal to one of these. And this quantity, our last lemma, is given that by this quantity that is here is exactly what we want. The integral of fys dy minus z. So what is the idea? Again, start with without the limit and try and we separate in 2 integrals. Okay, and here again a lot of inequalities, Holder inequality, Jensen inequality, and inequalities for the kernel or for the exponential for this quantity in the case of the Gaussian kernel that we are trying to get. Okay. So after a work, okay, So it's Holder inequality of the exponential, inequality of 1 over x exponential of x or minus x squared, and then Jensen inequality give us that the coefficient that we are putting in the epsilon is positive. This is the main thing, okay? You can do it a lot of inequality, but trying to get the best inequality in order to ensure that this quantity is positive wasn't so easy at first. Okay, so this is the proof, this is the theorem, this is the main result that we were able to get it. So how about the motivation? Because the motivation, as I present, okay, so this is the proof, whatever. But our motivation was trying to work with this kind of equations, with fractional Brownian motion or Holder process, but with sigma, not with a Lipschitz condition or linear growth, a little bit more coefficient with discontinuity. Okay, so okay, and of course with the forward integral. This is the main thing here in this work. Okay, so we work with sigma. So with sigma plus and sigma minus, both positive, cannot cross 0. And we say, okay, what happened? We know that because we proved the existence and uniqueness in the case of the integral is the generalized Stiglitz one. So what happened if we work with the forward one now? Okay, what happened with this simpler equation, but with forward one? Okay, so again, our Lamperti transform is the same, and lambda to the minus 1, you can compute by hand, very easy. But then, okay, you say existence, okay, but in the existence of the solution of this equation, then you use the theorem, because particularly you want to change dys minus by this quantity. And then you want to say that this is exactly xt. So defining xt by this process, ys is, for example, your fractional Brownian motion or your process with Holder continuity path. So if you define x like this, then you can ensure, because you get the theorem before, by this quantity, so xt equal to lambda to the minus 1 ys plus lambda x0 minus y0 is a solution of this equation. Perfect. We get a solution easily by using our theorem. Okay, so that I said, lambda to the minus 1 of this process is a solution of the equation. And this is the same solution as if you change forward integral by generalized Stiglitz integral. Okay, so what happens if you have other solution? So we can get uniqueness. We know in the case that generalized Stiglitz integral, you have a uniqueness, existence and uniqueness. So in this case, we can ensure uniqueness. Okay. If we assume, if we assume that the solution, we know the solution, first thing, is lambda to the minus 1 of yt, okay? So we know that this is an increasing function, lambda to the minus 1. So if we work with all of in the space of all of increasing function on R, we can ensure that exactly G is the solution of this equation. Suppose that we have other solution that we call G, but here we need a little bit more. So we need to assume that for all m, this probability and this probability are strictly positive. Why? Because we need to cross m. We use a mean value theorem in order to ensure that we can get it a little bit more than this. So we need to pass from 0 to t to y0 to yt. So of course, for the fractional Brownian motion, this is true. So again, if you assume that you are working in the space of all of the increasing function, then you can ensure that g of x given by g of yt in this case, a solution of the stochastic differential equation given by this forward integration is exactly what you want. That means that satisfies lambda gx is lambda x0, the integration of 0 to x of this quantity, and this is exactly lambda x0. So again, you get the uniqueness by using our theorem that combine the way that you compute this integral. Okay, so more or less we knew that we can get uniqueness and existence with a coefficient that have a discontinuity. Of course, we can generalize for more discontinuity or a finite number of discontinuities, but the problem was that we cannot cross zero. Okay? As I said, everything is positive, sigma was positive, so the problem to cross zero was a problem in order to ensure existence and uniqueness. Okay? So the second application or the second example was what happened with the sign. Okay? In the Brownian motion, the sign is you have this equation with dB. What is the solution of this equation? In law. Brownian motion, right? Okay. So we know that the Brownian motion, and this is very easy because we use quadratic variation. Okay. And the quadratic variation is exactly that we want, that is T. So exists a probability space that solve and a Brownian motion that solve this equation. Okay, but this is completely different because here we have the sign, here we have forward integration. So what is what you think about this equation? Do you think existence and uniqueness? And I said that we have problem to cross zero. So what is the intuition here with the sign? The Brownian motion get existence is in law, so it's very weak. So, okay. So our intuition was that we are not able to prove uniqueness here in the case of forward integration. So then, okay, we try, of course, and since we couldn't, so then the next step is try to say, okay, there is no uniqueness in this equation. And the second step is try to find more than one solution, or try to find a kind of representations of solution of this equation. Okay, so again, remember that our theorem is involved to this kind of integral that we want to use somehow, but here we want to use in order to give a representation of the solution of the equation that we are trying to understand a little bit more. Okay, so we said sigma t is the infimum of sigma t is the infimum between S between t and capital T. When x, suppose that x, little x is positive, then is the infimum of f. So between t and t, so suppose that you are here, where x is equal to 0, okay? And infinity otherwise. Okay, this is a nice representation given in an old paper, so we keep it and we transform in something that we could get a nice representation in this case, okay? And y infinity, lambda is the sub between 0 and t when x is equal to 0. So what happened is never cross. Well, it's never cross is 0. Then, of course, we say that a never cross 0. That means that in this case is all the time positive because never cross. So if never cross 0, this is 1. And then it's yt. So that we use this information in order to get for what's happening in the infinity. Okay, we get this after we try to get some solution of this equation. Okay, so what is the proposition that we get it here? In the case of the sign, if x is a continuous solution of this equation, then the absolute value of x had this representation. Okay? So, in any case, we have some representation given by this sigma t. Okay, so we have a representation of the solution of the sign that at first was more or less that we knew because in the Brownian motion case there is a weaker solution. So we are not surprised. This proposition wasn't surprising us. So let's do an example about this equation. So of course we put little x equal to 0. So our first solution z is equal to 0 is a natural solution. And in this case, in 0, sigma t is equal exactly t. Okay. And lambda is capital T because it's the sub. Okay, this is an easy solution. So, okay, so, but other one, okay, not the simple one. So Z2 is, you know that we have our representation, okay? So Z2 now is yt, when yt is positive. It's also a solution of this equation. So again, we have our particular case when the x0 is equal to 0. So, okay, we use sine of Z2, okay, dys. And in order to get that these equalities, we use our theorem. And then this is actually y plus, that is yt if yt is greater than 0. And this is exactly Z2, okay? So it's very easy that you get this, but first you have to prove that this equality holds, okay? Okay, so and sigma t is yt is less than 0, and this infimum that we don't know what it is, if yt is greater than 0. So again, we have a nice representation in with the forward integral for this SDE with that singular coefficients. Okay, there is a DE with more kind of process that you can put here that are singular with discontinuities, like in the Brownian motion case, and you can get representation for all. It's a nice exercise to change the sign to put, for example, what happened with the indicator of xs equal to 0, or other kind of function here that is not Lipschitz or linear growth or this regular kind of coefficients. So using the way that you can pass from here to here, you can get it a representation in some specific cases. So, and finally, I think I have a lot of time or not. What's it? It's okay? Ah, perfect. Okay. Finally, there's more than this reference, but I want to show you. First is the paper of Rousseau and Valois about the forward integral. This is the paper by Lauri Vitasari, Leskela, and Cheng, the pathwise tilted integral of discontinuous evaluated stochastic process. Okay, and those are our works in 2017 about fractional SDE with discontinuous diffusion coefficients. And the last one is that we are presenting today, that is the forward integration of boundary variation coefficients, that is, will be appearing when you. So that's all. So if you have questions.
We have time for question. Any question?
As far as I understood correctly, everything is happening in one dimension because I guess the Lamberti transform is working well in one dimension. Like first, can you extend this somehow to multiple dimension? And the second question I have is, I hope you didn't answer this throughout the talk. Like there is a lot of theory when you have additive noise and you have a bad drift. And usually I thought the Lamberti transform like transforms a multiplicative equation to an additive equation with additive noise. And can you somehow use the theory of singular drifts and just transform your equation and use the theory to get a solution or uniqueness?
Okay, so first about multivariate process. Okay, we didn't because we didn't, I don't know, maybe we can generalize. I don't know if this is or not, but at first, I have to tell you something that at first we work with the equation with the sign. We start with this equation because we try to understand what happened with other kind of integration with the equation with the sign. So it was in the one-dimensional case, okay, especially. So then we get a more general result in this way. So could be, I don't know what will be the problems inside in the computations. Maybe, I don't know, maybe the kernel that you will use in order to get the probability, but and a lot of inequalities inside. I'm not sure, but maybe. And the second question was why we don't use something like transformation of the...
Yeah, to get like something with additive drift and use the theory about singular drift. With additive noise and use the theory.
But you need, what do you need in order to transform the equation? Sigma is discontinuous.
Yes, I know, like it works. I only know the case for when it's smooth, but I wondered if you have something similar for these discontinuous.
No, I don't know. We use the Lamberti transform in the case of discontinuous, but not for get a nice equation in order to get exact solution, one solution of the equation, which is Lamberti transform. But I don't know what kind of transformation we use in order to get outside sigma and pass through to the drift term. But maybe only I can say is that you can approximate sigma and then pass through some transformation and then go in this way. Yeah, maybe will be other idea.
Another question? Comment?
So in your theorem, you need alpha bigger than 1/2. And so I was trying to think where in your proof you actually need alpha bigger than 1/2. And one place I think is critical is when you approximate by this epsilon approximation. And when you look at the derivative, there is an epsilon 1/2 factor. And I was wondering whether this epsilon 1, this is the exponent 1/2 in the epsilon is the one that makes your theorem holds only for alpha bigger than 1/2.
Good question. Maybe there is an inequality, a better inequality, but for sure we didn't found it. But when you use the holder, then you get the alpha or the H minus rho. Then you get inequalities for the kernel, okay? And then you get by Jensen, after that all, I mean, the lot of inequality, then combine it with Jensen inequality, you have to be sure that you can pass a little bit to the epsilon in order to get epsilon positive in your inequality. So this is the inequality that, if I remember well by myself, is an inequality that you have problem with alpha greater or less than 1/2, that you cannot use it. But there is some inequalities inside of that I show here. There is more inequality that you will use it. So, but I think we did the optimal kind of inequality for the kernel, for the Gaussian kernel. So the holder is passed through with the Jensen inequality, with LP. We didn't prove probability because we cannot change limit, but we did it by LP. So maybe no, maybe what you just is the last inequality that you have, you get a problem inside.
Another question? Thank you again.
Paulo. So, professor.